Meu colaborador que está aqui no Brasil, tá? Então, primeiro, boa tarde. Gostaria de agradecer a oportunidade ao Fórum de Sistematica e Evolução, agradecer ao Caio Neto pela conexão com a Marina, que proporcionou a possibilidade de nós trazermos o professor Peter W. Lucas, em apresentar parte do seu trabalho nessa tarde. Tá, o professor Peter, como ele mesmo vai apresentar, ele tem trabalhado já há mais de 20 anos com anatomia funcional de primatas. Então, eu vou deixar para ele explicar realmente o que ele faz, que ele vai ser muito mais preciso. Tá? É uma grande oportunidade, é a primeira vez que Peter fala aqui no Brasil. Então, nós estamos muito honrados de poder trazê-lo para falar aqui no Museu de Zoologia. Tá? Então, obrigado. Eu vou passar direto. So, I'd like to introduce you Peter Lucas. Please, Peter, maybe you can introduce yourself better. Okay? Thank you.
Well, I thank you very much indeed for inviting me to speak. That really is a pleasure for me, because as Mauricio was saying, I've been here several times, and I always wanted to meet more people in São Paulo interested in zoology as a whole, even though, I suppose, like everybody who enters a museum, I'm a specialist. It's terrible, isn't it? It automatically means how many people are you going to relate to. But I suppose I've spent my whole career really working on teeth, and that's what I'm going to talk about today, because I'm a specialist, I suppose. So I can't really get out of that. Also to say that normally I would talk with a tablet, but just rushing away here, maybe nerves, because I'm speaking English, I couldn't get the tablet to communicate with the projector, so it's now in Microsoft Word instead of something I can write on. So anyway, if you're filming it, I hope it doesn't disappoint you too much. All right. I'm billed as being from Washington, D.C., George Washington University. That was the last place I went to. I've actually been a bit of a traveller, but I started in London, and I wanted, rather than make some sort of visit to a country where they had primates, the animals I was working on, I wanted to actually live in a country that had primates and not be so colonial, if you like. So I went to Singapore. And I spent 9 years in the National University of Singapore at a time when research was very difficult. Very little money, very little equipment. Nowadays it's a very big university. I don't recognise even the city when I go round it. I had to leave there due to a slight dispute with the presumably incoming head of department. So I moved to Hong Kong, which was nice too. But then I moved to Washington, D.C. I didn't really get on too well with America. I was too used to Asian, or I think also because my wife is Latin, very open and relaxed style of communicating with people. I didn't really find that in the US. So I moved, and for my tried to get back to Asia, but I'm already beyond retiring age in much of Asia. Singapore retires at 55. 55 years, that's it in Singapore. They may have changed it now, but that's what it was like when I was there. So I've gone to Kwait, a very different place, but the research I'm going to give now was entirely done in Kwait. And, well, you see what you think. I think it's appropriate for Kwait when you see it and see what I've done. So, many of the co-authors coming up now in this movie kind of environment, so it will be scrolling. The first 5 people, all Kuwaitis. First one is a dentist, Ridwan Omar. He's one of the people who basically invited me to go. He's a dentist. I'm not a dentist, but I'm in a dental faculty. And the next 4 are all engineers, and I've always tried to work with engineers. I really like the way they think, and they can offer, particularly for something mechanical like teeth, can offer a lot of nice solutions to things, hopefully quite simple. We had to get some material for this study on tooth wear, and we got it via someone I used to know in Washington, D.C. She was working at the Smithsonian most of the time. She's now in the Max Planck Institute in Leipzig, and that's a technician. And we had to have a theory. And the best theory I know, and it's a brand new theory of wear, is by this guy, Tony Atkins. He's a retired professor. He works now mainly in Imperial College London. So that's the sort of cast of characters, if you like, the people involved in all of this. So the first thing I'd like you to consider, and I think I may have to just put it down in size a little bit to do this. Whoops. Oh, I didn't mean to do that. I shall watch out for that. Is, what is tooth wear? Well, tooth wear to most biologists is actually a lot of marks on something, wear. But actually, officially, it is the loss of tooth tissue volume, the loss of volume of something. You had to have lost something. Something must have left the surface. not just be a changed surface, it must have left it. What causes it? Well, I sit in a dental faculty, and most of them seem to think that it's largely chemical. I think that is because of the way in which our teeth decay nowadays. That influences them. But they all say, no, it's a chemical process by and large. I disagree with them. And like most biologists, I treat it as physical causes of wear. And the word abrasion comes up in English. And I think you have the word abrasion, abrasão, is it? It's very similar to Portuguese or Spanish. Use the same word. Why is it important? Because there's now getting much better evidence in mammals anyway, that for many mammals, when their teeth wear out, that's the point at which an animal dies. Now, I talk to people in other body systems, they say, well, the lungs give up, the heart gives up. What's special about teeth? Well, what's special about teeth seems to be that wild animals die long before the other systems give out. And what is coincident with it is the teeth have given up. And there are many studies, for example, now developing, where they look at the efficiency of the dentition. And as the dentition wears, the efficiency goes down in terms of things like ability to break down particles. So I was taught it when I was young, and I still believe it, that basically a very common reason for animals to die in the wild is because their teeth give up. So that makes tooth wear very important in a selective sense. Is this okay? Yep. I won't make a joke because I'm worried about it, but I might do a little bit later. But when I make jokes, I tend not to smile. So if it sounds funny, you can do it, but I tend not to smile myself because I've heard it before. There's a subject called microwear. It's gone across the whole of vertebrates, dental microwear, but it really started in primates. And it says that this is how you study wear. You take some sort of image of a tooth surface. In this case, it's dental enamel. This stuff that contacts fingernails, much of the time. You look at it, and you see a lot of marks on it. And they used to call these marks scratches, and these other marks pits. And this isn't very clear. From my point of view, I can't tell much about what have caused this from this level of image of it. But it is the currently accepted best way to study dental microwear. That's the scale. About 10 microns is the scale bar. This is a howler monkey, and it's not done with a scanning electron microscope. It's using an engineering technique called white light confocal microscopy, real-time confocal microscopy. And the problem with it is it can barely make out any of the elements. And instead of looking at individual scratches and their features, which is the way I do it, the way I'm thinking of it, they tend to look at a whole texture and say how complex it is, and whether it's oriented like this, or whether it's scattered in all directions. Before they decided to use white light confocal microscopy, they used a scanning electron microscope. Now that is capable of really resolving any of these features, but it can't resolve them in 3 dimensions. It can't see anything about the form of any of these features, or whether things are raised or anything like that, because it's only ever looking in a 2D pattern. We see some scratches here at higher resolution, and we see some great big pits. And for the longest time it's been said that this can tell you about the diet of an animal. Lots of scratches, particularly scratches like this coming up now. And this is a gorilla. In parallel like this, it eats leaves. What sort of leaves? Well, we don't know, but it eats leaves. That's the level of it. If you find many pits, then it's evidence they've been eating harder objects. And it's all done based on statistics, correlation. If we know an animal eats hard things, and we find lots of pits on it, and add that up across lineages, across species, we say that's what they did. For me, these are important questions as somebody who's interested in teeth as a whole. They may not be the questions that have often been asked, but they're what I would ask. What sort of forces are involved in making these marks? I'm very interested because they're all so small. You don't find very big microwear marks. You do find some bigger things called chips on teeth, but they tend to be rare compared to these very, very small marks. And most of these marks seem to be linear. They seem to be like scratches rather than pits. In other words, there's been some sliding along the surface. Why is this? And for me, none of these features are actually wear. For example, I could go in and I could actually make, I won't, but I could make marks in this, I could make marks in this, and afterwards you could see my name in it. But if you weighed it, it would still weigh the same, so it hasn't lost any tissue. I didn't take anything away with me, but I did damage it. So they're talking about damage, but they're not necessarily talking about wear, which means loss. And what happens to an animal in the end is not just that the surface changes. Stuff it's wet, its tooth material's gone. Now, scratches predominate over pits, and there are two types of scratch that I'm going to talk about. The first one is actually what I would call abrasion. We've got something coming along here, and this, when it was drawn in 40 years ago in Scientific American, was about a tool, something like a chisel. Do you know it? Like a chisel? Like you use in woodwork to remove material. And it lifts it up. It takes off a chip of material, and that is what I would call abrasion, because abrasion is the loss of material. And compare this to another situation where it's made a mark, it's made a groove, but nothing's been lost. Instead, it's been piled up. Material's been piled up, and it like pushes a wave in front of it. And this, in mechanics nowadays, we call rubbing. As far as I can see, the best term for rubbing is esfregar. Esfregar, to rub. And that doesn't mean anything's lost. But these are two alternatives. This one, there will be no wave. There will be no build-up around the side. In this one, there will be. That's a very good clue to what sorts of things could cause this wear straight away. And this comes from tool research. Now, there's a key contrast then between rubbing, esfregar, and abrasion. Sharp objects tend to be the ones that abrade, so they have to have a sharp angle on them. Blunt objects always tend to rub. And if you've got abrasion, you've got direct wear. It's very quick. Pieces will be lost quickly. Rubbing will not lead to direct wear, but if you rub for something long enough, if I was to be here like this, and you were to come back next week, and I was still doing this, well, I would have lost part of my finger, so I've worn my finger, but I also lost part of your speaker here like this. So rubbing does produce wear, but it's very, very slow. And it can't be the major reason, I think, why tooth tissue gets lost so easily. Is there a solution to this, rubbing versus abrasion? Can we say when one happens and when one doesn't? This is the contribution of Tony Atkins. Is this going too slow? Okay. Sorry. Oh, sorry, you'll pick. So I don't want things to go on the web. There are some physical factors you need to know, but Tony Atkins has a solution to part of this. It's only for one particular shape, because this is really complicated, the solution involved. It depends on the toughness, in this case of enamel. Toughness seems to translate into Spanish or Portuguese as dureza, and it means the ease at which pieces are lost. It doesn't mean how hard something is in terms of whether it's firm like this or not. It means the ease at which things are lost in terms of the work needed to lose unit area of crack. Something called the shear yield stress, which is very close to hardness in its firmness sense. You measure this, but actually the factor involved is this, but they are very simply related in most materials. Friction, which I think is the same thing, a coefficient of friction. And the depth of contact, the depth to which... Oh, sorry, in the wrong place. Please. Yep. Move. The depth to which anything will go in. Now, this is our particle, and unfortunately our particle has got rather a convenient shape. But it's the only shape for which there is a theoretical solution. So we have this particle moving along, and in this case, it's making a wave, which we call a prow. You can see this wave in front of it. Dependent on all these angles, of which this is the only critical one. The particle is moving this way, and this is called the attack angle. It's So there are some analyses of tools that relate to this, but the attack angle itself is new. Provided the attack angle is correct, then instead of that happening, there's no prow, material is lifted away or chipped off. And for any given material, if you know its characteristics, and this is drawn for the properties of enamel, produced by a rigid particle, we can work out for a given force, and these forces are very, very, very low, and for given friction, which just by luck for enamel makes no difference, we can work out what sort of attack angle a particle needs in order to remove tissue. So this is the solution for two equations that come together at a transition. And if a particle has an attack angle larger than this, it can remove material. But if it's smaller than this, it will only rub. And just by luck, the transition angle between red for high friction or blue for low friction is exactly the same. So friction itself, you don't need to know. In our experiments, we do know friction, but we don't actually need to know them to work this out. And if you think it's going slowly, I'm about halfway through, so, which wasn't a joke, so you didn't need to laugh. So theory predicts an attack angle. It applies to sharp abrasive particles, but there is another corollary. And this is the difficult thing, and this does relate to some things that do resonate with microware people. It only works if these particles that mark enamel are rigid compared to the enamel surface. And there's a definition of a rigid plastic contact. We need to know whether it applies or not. There is no theory if it's not rigid yet. That's being developed. If the hardness of a particle in terms of its firmness is more than 2.5 times that of a surface it's pressed again, so this is a potentially abrasive particle against enamel, if its hardness is more than 2.5 times of enamel, it can abrade if it's got the right attack angle. Otherwise, generally, it's only going to rub. So one of the first things you want to do is look at the types of particles that have been suggested to mark teeth. One of the first is dust. And I said this was a Kwait study, and we looked hard for dust, and then we found it all around us. It's a great place to work on dust if you live in Kwait. And it was said about 50 years ago that this was the hardness, take it as 7, this is a unit, 7, of dust. Plants produce silica in abundance. They're called phytoliths in general. And Amanda Henry in the Max Planck, and previously at the Smithsonian, under Dolores Piperno, is a specialist in that. And it was said 50 years ago, but it's been questioned since, that the plant silica, because it's amorphous, it's got holes in it, and it's hydrated, is only about 5. So it's less hard than quartz. Plant tissues, the hardest plant tissue known, we did and published at the start of this year, and we have 0.4. Now compare that to enamel. In different animals it's somewhere between 3 and 6. None of these particles would be rigid compared to enamel, and the hardest plant tissues in themselves are going to be way below it. Bone, and this is enamel, dentine, are nowhere near it. They're about 10% of this. They're not going to do it either. So what on earth is wearing teeth? Maybe none of these particles are rigid. Maybe teeth always just get rubbed away. Maybe that's how they survive so long. It's clearly necessary to be very accurate. So going beyond nanoware, we're solving this by going beyond microware, we're going into nanoware. This is what we did in poor old Kwait that doesn't do much research. Shall I go offline? There's not much research done in Kwait. There's not? We did nanoware. And some of it is straightforward, and you could easily do anywhere. Some of it is new, and if you know how to do it, you could do it anywhere. To start with, we did what a conventional nano study would do. We took a nano indenter with a diamond of Berkovich shape completely rigid, to find out what the hardness of these particles were. We looked at two types of phytoliths, courtesy of Amanda Henry. Some that came from the skin of a fruit, squash, and some that came from grasses. So we've got values for them. And they're much lower than 5, which is given in the literature. Some of them do get up close to 5 because they're obviously very variable. They're not of a very standard composition. Very variable indeed. But they're nowhere close to what was assumed. Enamel. This is the enamel we used in all our experiments. It's mid-enamel because that has variations in properties. But in general, they're way below it. And these types of phytoliths don't even overlap at all in properties with these. And here is quartz dust. The value of 7 in the literature is completely wrong. It's somewhere between 12 and 14. It is over 2.5 times as hard as enamel. It is rigid against enamel, and it's going to rip enamel to pieces. And as I'll show you in a minute, it can rip enamel to pieces at very low forces. So a type of informal experiment that I do in Kwait, which is walk out on a very bad day with my mouth open, come back in, is liable to be causing me extensive tooth wear. It was a joke. So it's shocking, in my opinion. The hardness of quartz dust that's been accepted in the literature is nowhere near correct. It is terrible stuff. But phytoliths, as suspected 2 or 3 years ago in a paper, are actually softer than enamel. And some of them, like from squash, shouldn't be doing anything at all, because if you're less than 2.5 times as hard, actually you shouldn't be damaging it at all. That's just numbers. Does it actually work? Does any biologist actually trust a theory of anything? You'd want to see practice. To do that, what we did, and this is new in any field as far as I know, is we took a nano-indented tip, we mounted individual particles of squash, phytoliths, of quartz dust, and, because I'll show you that enamel gets lost when quartz contacts it, we did enamel on enamel itself. Individual particles, and we mounted those and rubbed them at known forces, at known friction, against an enamel surface. That, as far as I can see, is completely new. If it isn't, okay. Here's a nano-indenter tip, and here is a single particle. I can't tell you which one it is because I can't. That's not the way you identify it. That step took us ages because that's got to be stuck there. It's got to be rigidly stuck there. You've got to know exactly where it is. And you might say, well, what sort of scale is this? Well, this is 500 microns, 500 micrometers. So this is about 40 or 50. You have to be sure you've got one. You have to get glue that will work. You can't have anything else in the field of view. And you must look hard at the geometry of this. And you must be absolutely sure what you've got. So once you've got it like that, without coating it, because you can't put any coating on it, you can't put gold coating, you can't put carbon coating on it, you've got to get it into a good enough SEM with energy dispersive spectroscopy and have a look and make sure you know what you've got. Well, I know these things well enough, and if this applies to this, there's silica there, which means it's got to be either a phytolith or quartz dust. But it's got calcium, it's got potassium in it, it's got some chloride in it. This is absolutely certainly a phytolith. It comes from a plant. So we can capture a particle, we can identify it. Coming in a minute, dust. This is a dust particle on the end of this very small nano-indenter tip. It's got a halo because the halo is the glue that we used. We have to make absolutely certain that the glue is not over the particle, only against its lower surface. That's before a test, and I believe this is 20 micron scale bar, and this is afterwards. It's been against enamel in a test. We know the conditions under which it's happened, and it's removed a whole load of material. And when we look at that material, This is under a light microscope. We look at this under an SEM. You can see actually it's lots of small enamel chips. So not only does quartz, just like that, remove bits of enamel, and the load here was 600 micronewtons. Now, when I just bite my teeth together, I could be producing easily 200 or 300 newtons. This is 600 micronewtons to do that. Almost no force at all. And it's ripping out and fracturing bits of enamel. Did it have the right geometry to do that? Yes, because here we have a single particle, and you can see its edges. And when you look at it from the side in an SEM after the test, you can see that it's got all the right angles to be able to do that. It's sharp, it's got the right angles to do it. That's why dust is so dangerous. Abrasion is proved, in my opinion. Phytoliths. You need another piece of equipment to be absolutely sure what you've got. The sorts of nanoware I'm talking about, you really need to be sure what it's done. This is a phytolith, and instead of showing you the effect in the way of doing it before, I'm going to show you it with an atomic force microscope scan. And the size of this scan here is about 30 microns across. And it's three-dimensional. And what's happened is a phytolith has gone into the enamel surface here, embedded itself, and then it's been removed after the test. It stayed on the nanoindenter tip. You can see the enamel structure. You can see here the prism sheaths in enamel. And you can see very clearly here the build-up at the side of this scratch, and you can see this wave in front of it, which we call a prow. So it's rubbed enamel. Hasn't removed enamel, it's rubbed it. And you can see, by going along here, you can see absolutely clearly the contour of that mark. And in fact, all those marks, because it's rubbing, are nearly all U-shaped troughs. Quartz cuts very sharp V-shaped valleys and very irregular. Phytoliths produce U-shaped troughs. So you get rubbing with U-shaped grooves. What about enamel on enamel? It's got to be there. You've got enamel chips there because any time you've got quartz there, you'll get it. And it is going to come up, and it is going to show itself. Please. It doesn't. There. Thank you. Thank you. Thank you. It was thinking about it, and it decided to trust me. Here's an enamel chip, and we rubbed it against enamel. And this one raised 3 marks. They're each of them sharp, we could tell. Produced 3 marks, but it doesn't matter whether they're sharp or not, because the hardness of enamel is the same on both sides. This is enamel from its parent. This is the parent that gave us this chip. And it marked in 3 separate little scratches, 3 or 4. Each one of them is like a flat groove. And the reason for that is simply because the hardness of the 2 surfaces are equal. So you find out what enamel tooth wear looks like for absolutely certain. It produces very flat grooves, and it's just rubbing. There's no loss of material. Doesn't raise prows so much as it simply flattens areas. This is almost the end. And then the rest of it is up to what do you think we should do with this? How could we use it to interpret diets or change the interpretation of diets? First of all, what you need to do if you want to do research like this is organize your material. Then whatever you've got to set them in resin and polish them down. And then you've got to find out what their properties are. Critical property for the particle involved is going to be its hardness. You need to know the toughness of enamel, and you should know the frictional conditions under which it acts. Doesn't matter much for enamel, but I'm only showing you enamel. If it was dentine, then it matters for dentine. Frictional conditions, whether it's high or low friction, matter for dentine. Once you've done that, and that's all you might say standard or been done before, you go down this route, which is novel. You've got to find a way to mount individual particles. In our case, we mounted them on a titanium tip. Oh, sorry, we've gone too far. 1 second. Once you've mounted them, you've got to work out what they look like. And let's see whether we can actually... And will it take us... Oh, let's see. Just for fun, just to see what we get. Oh. See, is it fun? Might not be fun. Might be a headache. Here we are, here we are, here we are. Don't know whether you can see these letters. I can, but then I'm closer, and I've got glasses on. Squash phytolith, I think I showed you. That I know straight away that's a squash phytolith. Dust, you'll find very high silica. You'll find some other elements, a wide range of elements, including those not associated with organic material, because dust is not pure silica either. It's not pure quartz. There are impurities in it. But very, very high silica peak indeed. An enamel obviously shows you calcium, phosphate, oxygen's in there too. Hydrogen is too low to be able to be picked up by these EDS methods. But if you've got those signals, then you know what you've got. Then you go and do your walk across enamel. And here we have a remnant of something that when we started to scan it, this is the flat enamel surface, flat to 20 odd nanometers. Here's a particle, and I don't know whether you can see, it's got a U-shaped trough like this. Now as soon as I see anything like that now, I know phytolith did that. That's a bit of plant silica did that. And it's left a little bit of in it like an iceberg, like a sort of Titanic type of look about it. And the last little bit you need to do, if you're going to do this, is afterwards, are you really sure you knew what had happened? So when it's relevant, you need to take your particle afterwards, and in this case it's quartz, and look at it. And you'll find in this case there's all sorts of little extra bits over it that weren't there when you scanned it earlier. When you looked at it, you can see all little particles over it. And if you look at them and do a dot test on one of them, you'll see that you pick up calcium. There's still silica there because it's quartz, because the background will still be picked up. But there's calcium. It's got little enamel chips all over it. So it did do the damage, and you can prove it in that way. If I just go down a little bit then, later that same year, because I've now got to look at some writing. What are we doing with all this? Well, for reasons that I said, I can't actually say what the paper actually that used all this says. One way or another, within a year or two, whoever wants to know would know. But we're really reinterpreting virtually everything that's ever been written about microware and diet. In some cases, you can substantiate what people have said. In other cases, you really have to doubt that seeing parallel scratches tells you eat this food, pits tell you they eat that food. And if someone tells you that hard food did that, then I think that has to be wrong, because we haven't been able to identify a single biological element, structural element, other than these phytoliths that have the properties that can do it. Okay? That's it. So I say thank you very much.
Então, eu gostaria de abrir espaço para perguntas, né? Qualquer interpretação você pode perguntar diretamente a ele, ou se for necessário ajuda, eu posso traduzir.
Thank you. I work with ants. Yes, and we use teeth wear as a measure of age, a relative measure of age. The ants I work with, they last for a year, a worker. They have no queens, so that's why I was very much interested in understanding the social behavior of the group, to see how they pick up one to be the reproductive, if they are all the same. But so it seems that the oldest ants in this group of this particular species, they act as foragers, even if they have almost no teeth anymore. So in ants, for instance, it does not relate to probably to death, because even as they, when they age, their teeth wears, but they still work as foragers. So it does not relate this actually. Also because ants seldom eat. Mature ants, only the larvae eat. So I would like to know if you have considered other animals, not only mammals. Of course, these are completely different teeth, completely different chemistry and structure, but in terms of function, if you have considered other animals as well, and not only mammals.
My world, as far as you consider have any training, would be vertebrate world. But we published at the start of this year, when I was looking for very hard plant objects or biological objects that I could compare with it, we looked at a seed, and this seed shell's the hardest plant object that doesn't contain any metal ions or silica that I could find, and therefore know it's only 10% of enamel. Some of these things are very relevant to dentine, but not to... but I'm staying in my vertebrate world. We looked at things that ate this seed, and one of them was a beetle, a scelited beetle. And we looked at the properties of its mandible, and I read something about metal impregnation of these tissues. And those beetles wore themselves out just by going through the shell. So they had about 3 millimeters of shell to go through. And in that period, the females, which were going in to lay their eggs, completely wore them out. But that's kind of like the limit of my world. I don't know much about ants of any sort. It would be intriguing to find out what the properties of those teeth are, those mandibles are, and what they're using them against. And rather than saying, I could predict or I'm going to speculate, sounds very, very interesting to me. Very, very interesting application outside of a world I know of. So it's intriguing that it has little obvious effect on their life chance. Okay.
Thank you. Just two quick questions. One of them is purely mechanical. The other is more evolutionary. When you talk about rubbing, it just occurred to me that rubbing may be a process that occurs over and over again in several layers. So once you have those irregularities caused by the first rubbing, the second rubbing may actually become abrasion because of the irregularities that will just chip off. So since teeth are subject to so much wear and tear, this could be like a cumulative process that will result in abrasion, even though the process itself is just apparently innocuous as pure rubbing. Is that the case?
Everything I say is going to get recorded, is it so? You're absolutely correct. It's an indirect effect. None of our experiments relate to that, but it is well known that if you rub, like me doing this for a week, you will lose things. And it's exactly that effect. You get prows building up, and they're gradually removed. But if you're looking at the mic, if you're looking without giving away what we're doing, in the sense of going online, you can find remains of those prows and everything. Even on worn surfaces, you know very clearly what produces them, even if some of it's been lost. So it's wear. It's not abrasion, because abrasion is actually the process of fracture, but it is wear, yes. But it's very slow compared to a direct event. How slow? I don't know really how to show, except by an experiment for which there would be no theory. It's just practice shows that, and you could... and these machines you can do hundreds and hundreds and hundreds of times, and it can move it over a surface. You could come back the next morning and see what you've got. And in fact, you can clean whole surfaces like that. It's one way in a nano-indenter to do it. You rub away to polish. They'll do that.
The other question is more like a curiosity. I'm a fish specialist, by the way, but my question is not about fish. It's after knowing all that you know now, which is obviously more than anyone else knows on the subject, do you think it is we can still believe the idea that these phytoliths, you say phytoliths, right? Phytoliths. Okay, phytoliths. They evolved as a response to large herbivore evolution to eat grass, or you think this is not quite convincing? Because I always thought, why the big herbivores? Why not grasshoppers? It could have evolved as a response to anything that eats grass, right? But with all this data, you think the traditional orthodox theory is still tenable?
I do, but I just don't think they're anything like as damaging as people have said they are to vertebrate enamel. To vertebrate dentine, they will be. And as I think I was saying in respect to what I was researching in terms of invertebrates, I don't find their tissues anywhere near the hardness of enamel. I can't find any record of an invertebrate tissue that's even more than around the level of a seed shell or slightly more. That's why when they come together, the mutual wear is quite vast. There's no doubt at all from experiments that have been done really only over the last 10 years that herbivores, when they eat grass, will induce phytoliths. The grass produces them in reference to the attack. And it's also known from these experiments that the vertebrates then are deterred by this. So they can detect their presence. But in fact, between our teeth, we can detect the presence of things in this order. So a phytolith may be of the order of 10, 20, 30 micrometers. I think those are significant sizes because those are sizes that we can detect between our teeth. When you get down to dust particles of 1 or 2 microns, the only way with my mouth open in Kwait and then closing them is the fact that they fracture. And in fact, we predict that these dust particles, anything over a micron in size, will fracture. Below that, they actually behave plastically, dust particles, and they don't fracture. But you can hear the fracture. So if you taste gritty food, you know it's gritty because you're actually fracturing those particles and they're doing terrible damage to your teeth. But so, in relation, yes, I do believe they are, phytoliths are induced as a herbivore defense. If it gets down to the ecology of, so was it against invertebrates or vertebrates, in terms of the biomass lost and all of that, I think it still tends to favour for grasses, for modern grasses, very often the large herbivores. I think the herbivore will be deterred even by the fact it can detect them between their teeth. And it doesn't know that they're grit. All it knows is a foreign body, and it may well deter them on that basis. And many herbivores, large herbivores, let's take camels, in which I have a special interest, simply because they're a large herbivore that are not very far from me, even though they are domesticated. They produce enormous amounts of saliva. And it's always been said that that saliva was for the forestomach of a ruminant animal, because that's the only source of fluid. But in fact, when we take in grit or phytoliths, one of the reactions is a heavy salivary response. It's been shown in many experiments. Simple experiment, take chewing gum, embed little bits of grit in it, and people produce enormous amounts of saliva. They're trying to clear the particles from their teeth. And I think this is something like what a herbivore would experience. But in some respects they're fooled, because the rate of wear involved for a mammal and its enamel would be very low. If it's dentine, then yes, they can do heavy damage to dentine, we believe, but we're still working on that. Sorry to be so long-winded. And I don't claim that I know anything either. Sure.
In fact, I work with fossils, and fossils are we have a lot of problems to imagine the kind of food that the species ate before. Of course, some fossils are really easy to identify. For example, I don't know, a theropod dinosaur, for example. You have a knife, and the teeth have a knife shape, and so you know that it's meat. Obviously, it's clear. But especially in crocodiles, that we are working now here. We have some kind of crocodiles from the Cretaceous here, from São Paulo State, that have a special kind of teeth with shapes that are really, really bizarre. And they have a really big wear facet. It's a wear facet, true, of occlusion of the upper and lower tooth rule. And we don't know, because these crocodiles are chewing properly, I think, because they have this occlusion. But we don't have a tool, I think. We don't have a tool to determine which kind of thing these animals was eating or were eating. You know, if they are eating plants, or they are eating shells, or they were eating, I don't know, small insects. I don't know. You know, because we don't have this kind of tool to determine. We made some microscope, electric microscope, the maps, you know, to see some microstructures in the teeth, but they only show the marks of abrasion, or you know, the size, the size, the way, you know, yeah, the direction of the scratches, you know. But this direction, I don't know. You said about the calcium, or the some kind of materials that you can find in these things. What to suggest that we can do with fossils in this case, for example?
It was very clear. I could say the opposite. Maybe I wasn't clear. I think if I were to look at the wear surfaces, I think I could help and say what sorts of things might have got between there. Also spent a lot of my career working on tooth shape in relation to food properties. And in fact, if there's anything that I've been doing with Mauricio recently, it would be on things to do with that. The physical properties of foods in other ways compared to the shapes of teeth that most efficiently would process them. Everything you say about those crocodiles, they have an occlusion, they have very sharp edges, makes it clear to me that that's very likely to be the soft tissues that they needed to actually fracture and break up rather than swallow whole. So maybe they were taking very large particles. But I can think of a whole array of things that would be important. These have got rooted teeth, like other crocodiles, because crocodilia, modern crocodilia, are the only reptiles really with properly rooted teeth. That's very important. Yes. The shape. Then I would be tempted to answer it by saying I could write down, thinking about it, I could write down a whole series of things that would tend to lead me to suspect that your idea for diet has some credibility. And these would be based on a whole range of references or things that I've tried to do that would relate to that. So I could help if you want, but offhand standing up here, I don't know quite what to say other than try and stick to my topic and say even the wear facets themselves would give you some clues. Particularly if you know in relation to, I know something about crocodilia, and they've got quite a variety of enameloid tissue, of enamel tissue. Some of them have got tendency towards prismatic enamel. Do you know whether that's true in your groups? This is work that I read. There's an MSc thesis online from University of Florida associated with Erickson's lab. And that's online, you can get hold of it. And it catalogues whether it's aprismatic enamel with completely without structure. And that is terrible, that gets abraded very quickly. Or whether it's got something on the way to mammalian enamel with the formation of these prism sheaths. That is known, I think, from some living forms. You could get some clues from that. And then there was also a recent paper relating that to bite forces. I don't know whether you'd have read that one, in Crocodilia. That was something like in PLOS 1, Public Library of Science 1. So these are things that occur to me. But I think a whole range of characteristics would help you there. But everything you say sounds very reasonable to me, and you're the expert. So all I would do is just offer ideas that would... confirm your hypothesis, which is what one specialist always says to another one. But if you have time to interact, I could help. That's all I would say. Thank you. Thank you very much.